Hi, thank you for joining me today. As I mentioned before, I will talk about explainable AI, how to use it, how to make it properly. What are the challenges that we face in these days when we implement machine learning models, and why actually should we use explainable artificial intelligence? Where we should use an explainable AI. So I have actually today quite a lot of slides, more than 100, but I will not go through all of the slides, but I will share with you if you would be interested in any kind of details. And also just a few Jupyter notebooks to show you, to explain a bit more from the engineering point of view, how does it look like. So just shortly, who I am, who am I? So Karol Przystalski. I'm doing machine learning for about 15 years now. I did a PhD in machine learning in 2015, obtained a PhD degree in 2015. Some of my research papers are published on skin cancer, so how to find skin cancer using machine learning methods and images. Currently working on also on other machine learning applications in medtech and in the medical diagnosis. If you would like to have any question after that, just drop me an email. The email is also visible on the presentation. All right. So what's actually explainable AI? What is it about? Just a very short theory before we go into the code and the cases. So actually, well, machine learning as a topic, it is currently used in many areas. When I started my PhD and also my company in 2010, it was very hard to really convince the customer to implement any kind of machine learning solution. Now actually everyone wants to do it, and not every time it's a good idea to actually use machine learning. Currently, it's actually used everywhere in security, in medical diagnosis, something that I'm doing currently. Also, you can combine it with other buzzwords like blockchain, for example, or test automation, for example. That's also one of the area where I am involved, because we have several developer open source solution for test automation using machine learning methods. Okay, so what is explainable AI? It's also known as interpretable AI and responsible artificial intelligence. So there are two actually topics that it's not exactly the same, but usually people use the three terms here actually as the one that actually is about to explain or interpret what is behind this model. Right, and there are actually some characteristics that is important for explainable AI, so understandability, comprehensibility, right? So it's about understanding not just the network, the architecture, if we obviously deal with a neural network, but what's actually going by details in the network. And if it's a short, very small network, then it's obviously easy to explain it. But if it's just a bit more complex one, then it's it became a huge problem to explain. So there are different kind of characteristics. So terms that are related to explainable AI, so understandability, comprehensibility. So how to interpret in a natural language, right? For someone who is not really an expert in machine learning. Or interpretability, to explain it, right, in a human terms, or terms to a human, interpret it and explain it also, for example, for the decision makers. And transparency. Transparency is also one of the characteristics of explainable AI. What does it mean? It's about also transparency is about the algorithms specifically. It's about what's going on in the method. And there are also other characteristics like simulatability, decomposability, and obviously algorithm transparency. I'll just go through because we don't really have such enough time. You can go into details after the presentation. So why do we use explainable AI, or for what is the group that we are doing it for? So for sure that for the domain experts. So let's imagine you have a doctor, medical doctor, and you have a skin cancer solution. So they want to know what's actually happening in the back. How does it work to get the diagnosis or get the information about the illness on the image. And especially if you are a regulated company, like a medical company or a fintech company, so you cannot actually have a solution that is not explainable, right? Especially in these two regulated industries. Obviously, for the managers and executive board members, they want to know what's actually in the back. How does it work? Data scientists, obviously, for debugging, for example, or actually any kind of user that is affected. You can think about a scoring method, credit scoring method, for example. They want to know how it does work in the back, and actually not only because it's regulated, but also because of the customer wants to know why the customer doesn't get a credit, right? And you cannot tell that actually the weight in this matrix is below 0, so it means we will not get a credit. You need to specifically explain with details how does it work, not only because it's regulated. So so the goals, it's about building trust, right? Building trust and build also a confident and robust solution that we know how it does work in the back. Obviously, machine learning method usually doesn't provide, are not really accurate, 100% accurate, but at least if we know how does it work in the back, so we know the exceptions, more or less, how does it work, why it's happening. Obviously, fairness is another case, and the privacy about the data. It's also another goal of explainable AI. The way how we can explain the model, there are different kind of ways. Obviously, text explanation, like with formulas, for example, that's not the most convenient solution. By the scientists, it's a common way how to explain it, but actually, a better solution is the visual explanation. That's something that people like to see it on an image. Okay, why is it actually network work this way or other way? And not from the architecture point of view, but from the prediction point of view. I will show you some examples on dog and cats in a minute about the visual explanation. We have also the local explanation here. If for example, the solution is too huge, we just take just a small part of it and try to explain just the small part of the whole solution, or explaining by example, like saying, okay, here is something on input, it goes through the network like that, and at the end, this is the result, but step by step. Always simplification is another way how to do it. Is simplify the problem, the bigger problem, and try to explain by a simplification. And the very important one, I think it's the most important one from all of the methods, is the feature relevance, so feature explanation. I will show you one example on the Titanic data in a minute, how features are important for the explainability of our method. So that's what I just said. So we show an example. Here you have an image. That's something that we will probably see in the next couple of years, or similar solution where the identification of the customer or the hotels or actually anywhere. How to explain how does it work in the back, and how to get to know why someone was not recognized. So that's one of the use case. Or here you have two images. One is a cancer. The second one is not a cancer. Right? I'm analyzing this kind of images for the last, I did it for the last 7 years. So I know exactly that the one on the left, so this one here is a cancer, right? And this is not a cancer. And many people can actually tell, saying, oh, that's the cancer because it's, I don't know, more black, for example. So we also want to know why is it happening. The doctors, if they take it as diagnosis, to telling, okay, that's cancer, that's not cancer, because they have some expertise. And the same with the machine learning methods. We need to know how does the decision, the prediction is done, especially in medical solutions. Here's an example of feature importance, I would say, but based on images. There is a quite well-known example of a machine learning solution that was designed some time ago to distinguish between husky dogs and wolves by some researchers, and they actually achieve an accuracy of 90%. It's quite a well, that's a good accuracy, right? At 90% to get to predict between two type of animals. That's quite good. But then they actually try to figure out, okay, why is it actually what is actually the most important feature? And they figure out, oh, it's not the ears, that it's not about the eyes, I don't know, the nose, or actually what's actually very typical for the husky dog or the wolf, but actually it was the background, because the images that they provided, the wolves usually, the images with the wolf usually it's taken, I don't know, in the forest, or for example with a snow in the background. And here, as you can see, the most important feature here was actually the background. So the snow. Snow means, oh, it's a wolf. Even it's a husky, because husky usually we take pictures, I don't know, on the street, at home, I don't know, in the park, but actually in the city usually. So that's why we should also know, even if we achieve a high accuracy, we should know how to explain how does the method work. Or here, right? That's another case about the Tesla car. Why did it happen? Actually, this person died because the person crashed it with the new Tesla car. Oh, that's something also very important to debug the method. Why did it happen? Actually, make the models to retrain the models and make it more robust. That's also why we have explainable AI. Or another type, but here it's not. Here it's not about. Here we had a problem with the security, but still, and the retraining. That's another case where actually you can see that something can go wrong, and we need to know what happened. That's a typical case of debugging the method with explainable AI methods. Or here the stop sign, for example, just adding one sticker change it totally when it comes to recognition by the neural network you have in autonomous cars usually. So that's something that might change, and the question is why it's changing. There are other examples. They are called adversarial attacks. I will show you some examples later. It's actually topic is a bit much more difficult, and the problem is that actually we don't really have any good defense method for this kind of attacks. Or here, like Amazon, right? Alexa telling to suicide the person who actually talked with Alexa, right? So that's also another case. Or here, Google. One mistake, even the big brands like Amazon and Google, they have enough data, but still they are here. Well, they fail sometime, right? Also machine learning, and we need to know why it happened. Again, right, in this case. So there are many such fails, and I can actually do the whole presentation just to show you fails, why machine learning doesn't work, or where actually machine learning failed. And this is where we use explainable artificial intelligence methods to explain how the method works in the back, to avoid possibly it's like testing and debugging the machine learning models. But not only, sometimes it's actually you need to do it because the company is regulated, so you still need to do it anyway. So for the fintech, for example, there are a couple of cases. First of all, it's regulated, so they need to do it. But on the other hand, well, it's also very important that they think about GDPR as well, which is quite a very important topic for the fintech. Data anonymization, for example, that's also something that they do on daily basis. I'm not saying only banks, but when I'm saying fintech, I mean also the wealth management, hedge wealth management companies, hedge fund, and so on. So all kind of fintech, and they have different kind of use cases. They use actually explainable on daily basis. Or in health tech, health obviously the meta comparison between one, why is this method better than the other one, why is it actually giving such a change, and obviously data anonymization and privacy, because for the data scientists, we don't really need information about the patient. We need to have the images. For example, if we do the image analysis for cancers, for example. And there are other challenges that we also have here in health tech when it comes to machine learning. Similar with e-commerce, understanding the customer, chatbots, for example. Why is this chatbot behaving this way, right? If you talk to any chatbot, you might had the high chance actually, to talk with a chatbot that wasn't really so intelligent, right? If it's not intelligent but doesn't behave super stupid or weird, then it's fine. But if it's like works like a tweet bot, like a Thai bot that was developed by Microsoft, then you will get into troubles. Okay, so there are two different kind of methods. So the black box methods and the white box methods that we have. I mean the machine learning methods here. A white box model is a method that you know exactly what you can easily explain what's in it, right? But again, it's not about the architecture, right? It's not about explaining. Let's say here we have a decision tree. It's not about how this method divided, but explain the prediction, right? So how it comes to the prediction of how it comes to the output at the end. And there are different kind of methods that are easy to explain, like the linear regression, for example. That's something that even if you have such an image, you can easily explain what's going on and why is this kind of a in this case, it's not a prediction, but that's actually it's a regression. So why is it actually this value here at the end? Because you can actually easily write as just one very simple formula. Or decision trees, right? You know exactly, because you saw the tree at the end. You know exactly what kind of decision is made here at each stage to get to the prediction. So decision tree is also a white box method. Means you can easily explain it, but it's only about decision trees, because if we go into random forest, a forest is a method where actually we have more trees. So we are using more than one decision tree. It might be too complex to explain it sometimes, because there are too many trees, too many ways to explain, and it might be a bit more difficult. And in this case, it is then considered not to be a white box method, but actually a black box method. All right, so let me show you one example, just to give you a better understanding. Black box, white box. Here we go. So let me start with a black box method. I hope you can see my screen now. That's a simple Jupyter notebook. You can see here I have built a very simple neural network with 1, 2, 3 layers, right? 1, 2, 3 here, and it's whatever optimizer we use, what kind of metrics you actually use also for the quality measure. So you see actually the accuracy is 98% here, right? So it's quite high. But because we have 3 layers, we have also the matrix that actually input, and actually also the weights that are well, each layer has a weight matrix that is actually this matrix. The values in the matrix are set during the training, right? In this case, we have only 5 iterations. But let's take a look here. These are the weights in the second layer, right? Second layer, and we are getting the weights. So take a look how many weights we just set in this model. It's very hard or even impossible to explain what actually the value means. what is actually this value means, right? Or a group of values. It's very hard to explain it. There are too many, and this is just only one layer. If we can also get the first one, the third one, and we will have more or less similar size of the weight matrix would be similar size of numbers that we need to explain somehow. It's not really possible. So this kind of a network, even it consists only of 3 layers, it is considered as a black box method. Okay, so let me show you another example. Here's a white box method as a decision tree, as I mentioned. Scikit-learn, and then after the training, here's where actually we are training it, and here we build visualize the tree. And even if you don't know what's the Gini index, right? You don't need to know what's the Gini index, but you know that there is an index, there is a feature x2, whatever the feature means. If it's, I don't know, size of I don't know, of the mole of whatever, then you know that the feature, if it's below 2.5, then it's going here, right? And you see all of the samples actually from one group. So it means, oh, okay, so if I take this value, take this decision, then I will get this kind of prediction, right? As you can see here, we have 3 classes, the orange one, the green one, and the purple one. And here you can easily go through the features and you can even replace it with some if statements in any kind of language, and it's easy to understand why is this prediction, why we take this kind of prediction and not the other one. We don't need to know exactly what the Gini index is, how is actually this index calculated. Just to let you know, there are more than just Gini index. There's entropy and many other ways how to calculate the indexes to choose the feature that we actually base on to make actually to divide the leaf into 2 new ones. So this is the difference between the black and the white methods. So you might ask, okay, because this is the decision trees are quite simple here, but the question is every neural network a black box model? Because this one consists only of 3. Obviously, if we reduce it to 1, it might be easier to explain. But in general, most of neural networks are black box methods. There are some exceptions I will show you in a minute, but in general, this is how, unfortunately, looks like currently. And most of the solutions that are developed are based on TensorFlow, Keras, that actually based on neural networks. Obviously, you can use neural networks to implement a decision tree. That's also a way, so that's explainable. But in general case, it's very hard to explain. So there are different kind of type of insights that you can get from Explainable AI. I will just skip that. Just go to next, because there are just too many slides. So what you can also do, debugging, obviously. So you know exactly what's happening there. And it's different like the typical software development debugging. You're not putting a breakpoint somewhere and check, oh, is this good enough or not, and then just run it or do some coaching. That's not how it looks like when it comes to machine learning. What you can also do, you can improve the feature engineering process. So it means maybe we need other features, or maybe we need to extract it in a different way. But this is something that you need to get to know when you actually try to explain the data, or the way how you collect the data. You obviously know how to inform your boss, for example, right? You're building the trust, you remove the bias, obviously, and another way is that you can get from Explainable as eliminating overfitting. That's quite easy to check if it's if you overfit. There are also different methods, not explainable AI methods, to find out if you're overfitted, but there are also explainable AI methods to find out if you overfitted as well. Debugging data leaks, for example, this is one of the way how you can find out, and obviously that's also about overfitting here. Another one's, all right, so let's move to the Titanic example. As you see, I guess most of you saw the movie. So if I would ask you, is there any feature, most important feature to distinguish if someone survived or not, you probably would say average female would be the person who has the highest chance to survive, right? You saw the movie, so you know what happened. But what can we do more about it? So let me show you one example. Here we go. They are not this notebook, the second notebook. Here we go. And just go back. Obviously, what you can do here is to analyze the data. And there are different kind of methods how you can analyze the data. Just to give you an introduction before we go into the Titanic example, here's an example of the Boston housing data set. And just based on a typical statistic analysis, it's called pandas profiling. Pandas is a tool to store and operate on data, bigger data. It's quite useful in machine learning. And pandas profiling is another solution for pandas to do static analysis of the data. Maybe I can run it. Here we go. This one to show you some of the results. It's quite easy because it takes just a few minutes to figure out that some features are less important than the other ones. And that's important at the beginning if you start the research, that okay, maybe I don't need all of the features. Maybe some I can skip some features, or there is a high correlation, right, between two features. I will just move down, and I will come back to the results when they are here. So there are obviously different kind of methods how you can prepare the data set. That's also something that is very important before we start. But that's actually a part of the typical process in machine learning. But what is important here, what I want to show you is about the data pre-processing, to know your data that you work with. Here I have an example of a data set with Titanic. The people actually who were on the Titanic, right? The name, the gender, the age, and some other information here. The class, obviously the label, right? If the person survived or not, and so on. So if you would now choose one or two features, probably would take, okay, the class and the gender would be the most important. But can we do better? Yes, we can. And I will show you that just in a minute. What we need to do first, before we actually go into an analysis of the current data, we need to drop the information about the string information, like name, because it's hard to make a list, a closed list from same names, because everyone has a different name usually. Same with the ticket and the cabin, right? Because that's not something that we can easy move to a number direct to the number. So we just remove it and take a look. Okay, just based on the other information that we have here, we have, using the logistic regression, you can obviously use another method, we have 78.7% of accuracy, which is not so bad. And here you have the feature importance, right? So we are actually here looking for a correlation between the survive, so the label, and the other features. And we see that, okay, the class is quite high and the gender is quite high. So our first prediction was the right one, right? Because we see, oh, that's highly correlated, and that's also highly correlated. It means we should actually think about these two. But let's take a look on the three features that we just skipped. So the name, the ticket, the cabin. Well, we can, what we can do, we can try to find out, okay, maybe the name would be something, or maybe there is something else we can find out. So let's take a look. Okay, maybe we can take a look if check the words, or split it and check how many words, what are the most popular words that we have in the names. And as you can see here, here's the list of the names, and then we count it and sort it by the highest value. So we see Mr., Miss, William is quite popular as the name. Okay, done. And we have also Master. All right. So maybe we can take this 3 here and here this one to take maybe this is also a value that can give us something to make a higher prediction, right? Because that's not a name, that's telling only what kind of person is it. So we can add new features here, right? Here, the 4 features with a 0, 1 value. The same with ticket. What we can do with ticket, not easy. So let's take a look what kind of strings we have. There's this kind of string like A or PC or STON like here, right? So probably this is a ticket seller, but I'm not sure about it. So that's something that we can think about. Okay, what kind of we have? Okay, we see we have this kind of. So maybe one of the ticket seller sold, I don't know, the VIP tickets, for example. It means this person has had a higher chance to survive. So let's add another features here, right? Here we have these new features. And what we can do with a cabin. The cabin, I think, might be quite important. Why? Because you know that the iceberg, it actually crashed into a specific area, in a specific, it started somewhere in the ship. So probably people who actually were in the cabins where actually the iceberg crashed into the ship. On one hand, they were lucky because they know that was the first one. On the other hand, they were not so lucky because they probably died because they know it as the first one. So I don't know what was actually the number of or what was the area now exactly, but maybe just using machine learning, we can figure out and try to divide the letter like A, B, C, and so on from the number of the row and take a look. Oh, maybe the cabin is also something that has an impact on the survival probability. So we see we have this kind of letters, and we just add the cabin letter here with a value 0 or 1. And now if we use the linear regression, we see, oh, we increase it by about 2%, the accuracy. That's quite good. Obviously, if we would use not logistic regression, but I don't know, SVM or maybe a decision tree, probably would get better results. But just adding new features will tell you a bit more about what actually is, what features might be important. As you can see here, the correlation is not only here you have the Mr., here you have the class again, you have this feature, this is also important. Obviously, the gender is important, but it's not the most important one here, right? Let's take a look on the cabin. Maybe the cabin is also very important. Well, what cabin was important? Yeah, this one, E, might be the most important, and G, probably it was or quite close to the place where it crashed, or maybe it was far away from the place, just an opposite side. So adding new feature, understanding the feature is the first step to understand the method, the model that you are building. And obviously there are also the performance, so the performance metrics, but I will just leave it for now. That's not the most important thing to think about now. Let me move back to the slides. Here we go. So who survived. Now you know more. You can actually, based on the Titanic example, you need feature engineering is very important to get to know your data and understanding your model that you build based on based on that. Yeah, the data collection, obviously, as I mentioned, it's just described here a bit more. So the black box method is something that we don't really know how it works in the back. So we put some data in and put some data out as the output, but doesn't really understand. Even if we know the architecture of the method, we don't really know how does it work in the back. I mean, how is the prediction made? An example, a neural network is a good example of almost any kind of black box method. All right, so survey, I will just leave it for now. So we have different kind of tools that we can use for that, right? And even we have a method to choose from. We have different kind of libraries like scikit-learn, for example. You have here the nice graphic from scikit-learn to find out what kind of method you should use. Actually, if you use scikit-learn, I mentioned here that actually there are different kind of solutions for building your model, for building your solution, and scikit-learn is one of it, is one of the most popular. And actually, scikit-learn methods are explainable. Most of it are explainable. Or actually, Keras and TensorFlow, PyTorch, they're used to build some networks. In most cases, they are not so easy to explain. So logistic regression, for example, explainable, k-means, decision trees, support vector, even a support vector machine is explainable, right? That's a matter where actually you find the highest margin between the two different kind of objects of different kind of class or label. And this is still explainable because actually at the end in the higher dimension, the way how we draw the line is linear, so it's easy to draw it, even explain with a simple formula. Or reinforcement learning, that's also something that is explainable because we have a matrix at the end, so we know exactly what kind of reward we get or penalty when we move from step A to step B. So that's also. So a GIM demo. Let me show you. I know we are running out of time, but let me show you one more. So the shallow methods, just an overview here. Here we go. So there are different kind of methods. Again, linear regression, you can draw it. Even if you see that there is no regression here, it might be that actually you can see it doesn't make too much sense for a linear regression. Sometimes you just need to put in the higher dimension like here, and you see that actually in a 3 dimension it is linear. I mean, it's easier to explain. So linear regression, or for example, logistic regression, right? That's also something that is easy to explain. Here you see doesn't make too much sense. It's very hard to divide it with a logistic regression, right? Not so good. But if you put it also in a different dimension, again, you get better results. So sometimes the feature engineering is not only about saying, okay, what feature is important, but also I mean, here from the feature importance and the visualization is important what kind of feature you take to explain it, like I show you here. So obviously Bayesian rules, naive Bayes, that's something that is easy to explain. Hold on a second. Freeze. Yeah, because it's a set of rules like here, right? So that's similar when it comes to the output compared to the decision tree. It's not a tree, it's a set of rules, but at the end, it's also explainable. And obviously, SVM is explainable too, that I mentioned you before. Here I have some examples that you might be able to run also at home, because I will share all of the materials with you later. All right, so I still have 100 slides, so let's move on. So there are some specific methods, so model agnostic methods to find out explain the machine learning methods. Here, by model agnostic methods, I mean here the explainable AI methods for finding out what's actually going on in your model. And there are different there are at least 3 groups, but it's changing all the time because there's a huge research now done in explainability. They're based on the features, right? How is the feature influencing the prediction or the explanation of the prediction? We take care. The second group is about the output. So we take care of the focus on the output. Okay, we take the output. What can we do with it, or how can we explain the output? Or, for example, we can explain the layers, the features from the layers. I will show you one example of a convolution neural network, which is one of the neural network that is explainable if you do it right. And when it comes to the model agnostic methods, the one that are based on the feature influence, there are different kind of names. I don't want to go into detail actually each method. We don't have enough time for that. But just to give you a better understanding of one here, you can see here that we have, if we take two features like the temperature and the predicted number of bikes, so we obviously want to know what is influencing the highest to the sales. So we see the temperature. Okay, here is the best temperature for that, and it's quite clear. The higher temperature here means more bikes. Then if it's too hot, then the sales of the bikes goes down. Humidity, right? That's quite important because at some point it's just dropping rapidly, right? So that's the feature that might be important for us to take into consideration when we talk about the sold number of bikes. Or the wind speed, right? When it's too windy, the sales is also dropping here. But I would say this one here is the most important because it's dropping rapidly here. Okay, we can think about the temperature as well, but it's quite clear that that's not something new. That if it's too cold in winter, you don't sell bikes, and the humidity makes sense also during the vacation time, right? And there are different kind of advantages of each method. Just to go through, because there's different kind of methods here to explain. Like here, for example, how to explain it. So there is a dog, right? So we just show the area of the dog, so the pixels, the super pixels. So the deep learning, I mentioned you that actually neural networks are hard to explain. So the last part that I have on my presentation is about deep learning methods, how to explain deep learning methods. Is very hard, especially as I mentioned, it's very the neural networks are easy to fool. I mean, we can easily fool a neural network, and our deep learning neural network is even more complex when it comes to architecture, so it's more not so easy to explain because of the complexity. And there are different kind of architecture. You can see that actually the deep learning methods, we are actually they are giving more and more better performance year by year, right? And now we have networks that looks like that. That's inception network. At all, it's very hard to explain it here at all, right? This kind of network. This is one of the modules of the inception network. But as you see here, not a bigger network doesn't mean that it's better. You can see here the VGG16, but actually the inception 4 is smaller here and actually give better results. But let me focus on the convolution network. I almost finished. We have it might be quite huge with different kind of layers that work like that. So it means we take the focus on part of the image. We can easily make an convolution network to give us information what part of the image actually at the end give us is the most important one. Here I have an example of an image representation with a convolution neural network. You see that actually some parts here are found on one image, on the second one, and just based on the relation, we see, we can find out that classify it as a pomegranate. But it doesn't need to be exactly the same. In this case, we have just this part, right? That say, okay, that's a pomegranate as well. And here I have an example of a class activation map. That's a method that is used on convolution neural networks where we see actually it's kind of we build a heat map. Here you can see by using gradients on one of the layer to find out what part of the image is the most important to take this prediction. In this case, it's the ear. Here it's the chest. Here I have another cases like here's a cat, here's a Maltesian dog. So different kind of objects will have different kind of, let's say, super pixels, or the pixels that are actually more important to get the prediction. The last thing really is about the adversarial attacks. Why we should use explainable AI. As you can see here, the image on the left and the image on the right, you see probably two pandas, right? I see two pandas, you see two pandas, right? But actually, we can fool a neural network that it will see here a gibbon. Gibbon is a kind of an ape. How we did it is add some noise to our image that is not recognizable by humans, but the neural network is able to recognize it. So that's something that we can do. We can fool the neural network, so it's important to find out how it's done. And there are different kind of attack types. I will just skip that and just show you two more examples. Here you have one pixel that change it from a cup to a soup bowl, or here the teapot. Just here one pixel, change it a teapot to a joystick. That's how you can fool the neural network. And explainability here is very important to figure out why it happens. And there are more and more cases, or you can even the sticker case. You can put a sticker just next to a banana, and from a banana it became a toaster. Right? That's the way how we can fool it. Or here, wear a picture and you are not recognized as a person anymore. That's how you can fool it, and explainable AI can be used to find out why is it happening. That's all from my side. It was a very short introduction to explainable AI. I have hundreds of more slides and tens of other notebooks in this topic. It's a very complex topic. I just give you a very short introduction to this topic. If you would like to learn more, I can give you some links to the resources. I will obviously share with you the slides and the notebooks. Feel free to ask any kind of questions. Thank you for joining today.